Okay, because NBC had 224, 213. Biden.
Biden has 238 and Trump has 213.
Okay.
But they should call North Carolina and Georgia today. There should be no reason they can't call those. Pennsylvania is not going to be till Friday. Alaska, they should call today. I've just been watching this map religiously. Maine hasn't called their other district one. I'm going to be so mad if they don't call them tonight. No, but I want them to. I don't think you're going to fight. I hope they at least call somebody. It's like there's no reason they can't call North Carolina or Georgia or Alaska. Because they're all almost all the way in.
Wisconsin had 100% voter turnout.
102% voter turnout. They had more votes than they do have registered voters.
Wisconsin? No, they have 3.6 million registered voters and 3.2 million voters. The information that I saw the same stuff. The information that they had was not correct. It was not.
I don't know. I've seen like different articles on that.
Information from the 2016 election of how many registered voters.
I don't know. It's wet.
The other, the 3.6 million registered voters came from the Wisconsin governor.
I don't know, man. He's got to win Wisconsin now. And Michigan.
Yes, Jacob, can you hear me?
Yep, I got you.
Okay.
I can hear you too.
As long as he wins Michigan and everything else he's set to win, he should be fine.
All right. Okay, focus on Zoom. The slides moving.
Yep.
Okay, good.
Yeah.
All right.
in quarantine. This guy's in quarantine and Oakley, and I don't know where
Or Andrew.
Andrew's normally watching it right now.
Well, it's 12:20, so it's time to begin. Good afternoon, all. We're going to talk about the heart. We're going to spend, hopefully, a good deal of time trying to ferret out the ins and outs of the heart. So let's have a word of prayer, then let's get started. And that's the problem. Okay, there we go. All right. Oh boy. Let's try this again. That's better. Okay. Now let's have a word of prayer and begin. Lord, thank you once again for bright sunshine, warmer weather, less terribly cold days and terribly windy days and flurrying snow and what have you. Thank you for this class, each person here. Thank you, Meredith is back with us. Thank you that we're hearing some people on quarantine had negative tests for COVID-19. Watch over us, please. Help us to live smartly and to bless and honor you in this class in every way possible. Amen. Okay. The heart, as we said, is divided into a left and right side. The blood from the left and the right side under normal conditions doesn't mix. If it does mix, there's some sort of pathology present. So it's separated by a septum. That septum forms gradually during development. As the baby develops, the blood is mixed between the parts that receive oxygen from the placenta and the parts that don't. So the baby is not moving that much. The baby doesn't need this huge amount of oxygenated blood. Once a baby gets outside the womb, that'll be another story. So the division between right and left sides of the heart develops gradually. If it goes awry, then you'll have mixing of the left and right sides. But normally, you shouldn't have that mixing because of the septum. So there are two upper chambers. The upper chambers are atria, lower chambers are ventricles. Ventricles are more muscular and bigger than the atria. There are valves that separate the atria and the ventricles. These valves are collectively called atrioventricular valves or AV valves. The AV valves are connected to the wall of the heart. These little cords are called chordae tendineae. The function of those is to prevent the valves from prolapsing, that is, bending into the atria. They're supposed to just close. If they prolapse, then they're not going to close properly. These prevent that from happening. The chordae tendineae connect to the wall of the heart via papillary muscles. Papillary muscles. The upper and lower chambers of the heart are separated by a fibrous skeleton that will functionally break the heart into two sections, an upper and a lower section. You don't get bleed through of the signal for the heart to beat from the top to the bottom. Instead, you have a special conduction system that conducts the signal to beat from the top to the bottom. Think of it as an extension cord, if you will, from the top of the heart to the bottom of the heart. There's no bleed through because of that fibrous skeleton. The fibrous skeleton also provides the structural scaffold upon which you'll make those valves and upon which you'll hang those valves, if you will. So heart muscle functions as a unit. That unit gets called a myocardium. Myocardium. The cells that form the myocardium are called cardiomyocytes, which is a bit of a mouthful. For sure. Painful to say and write out all the time. You'll see them sometimes for cardiomyocytes. And again, the myocardium of the atria and the myocardium of the ventricles are functionally separated because of that fibrous skeleton. So the fibrous skeleton has these two holes, and those holes form these rings, and those rings will provide the scaffold upon which you'll hang the heart valve tissue. Many students think the heart valve tissue is itself contractile. It's not. It's a very different tissue. It doesn't contract, it responds passively to pressure differences. So those rings are called annuli fibrosi. They will surround the heart valve openings. They'll provide the substratum upon which you'll hang those heart valve flaps. Let's look at circulation very briefly. So circulation begins in the right atrium. Venous blood gets returned to the right atrium. You have an inferior vena cava, superior vena cava. Both of these feed into the right atrium. From the right atrium. And then this is venous blood. So it's come from the tissues, so it's relatively depleted for oxygen, relatively enriched in carbon dioxide, relatively speaking. It's not that there's no oxygen in it, it's just been depleted for oxygen. From there, it goes to the right ventricle. Then from the right ventricle, it gets pumped into the first great vessel. That's the pulmonary artery. Now, the pulmonary artery branches to a right and a left. So before it branches, it gets pumped in what's called the pulmonary trunk. The pulmonary trunk. And then it branches right and left, and then those branch to the pulmonary arterial tributaries. Those will eventually branch and branch, branch and branch. They become the very delicate capillaries that surround the alveoli of the lungs. There, oxygen is exchanged for carbon dioxide in the alveoli of the lungs. Now, that blood will return, and it will return to the left side of the heart. Returns via the pulmonary vein to the left atrium. So that circuit from the heart to the lungs and back, that's called the pulmonary circulation. Pulmonary circulation. Pressure within the pulmonary circulation is low. It has to be low because those vessels in the lungs are delicate, small, fragile. If you have too much pressure on that right side, you're going to blow those up. You go from the left atrium down to the left ventricle. From the left ventricle, you go out the aorta, which is the next large vessel. It's the largest vessel in your body. And now begins the so-called systemic circulation, the systemic circulation. So that oxygen-rich blood will now supply your organ systems. That's your systemic circulation. The aorta comes up, makes a U-turn. There's branches that go up to the head and the upper extremities. Then it goes down the body. That's the descending aorta, dorsal aorta. Different books call it different things. In humans, because we're upright, tends to be called descending. In dogs, cats, it gets called. And that's your systemic circulation. So if we were to pretend this is a coloring book, and you were to use your crayon, and you're going to color systemic circulation, you would hopefully color from this part here, and then these parts here, and then these parts back to the heart, and so on and so forth. That would be your pulmonary circulation. Then, if we asked you to color your systemic circulation, hopefully you'd color this, and then all of this. That's your systemic circulation. Systemic circulation. And we go from large arteries to mid-sized or small arteries to arterioles to metacapillaries to capillaries to venules to veins, small veins, then medium veins, larger veins, and then the largest veins of all, these vena cava, inferior, superior. So hemoglobin. Hemoglobin, remember, changes conformation in the lungs. It takes up oxygen. It gives up CO2. Then, when it goes to the tissues, now it's in a low oxygen environment, changes conformation back, and it tends to give up oxygen. By giving up oxygen, taking up CO2, feeds the tissues oxygen, takes up their waste product, it to the heart, which pumps it to the lungs, which then releases CO2, takes up oxygen. So your capillaries are going to feed tissues oxygen, glucose, hormones, amino acids, other types of things that those tissues will need. They will eventually merge into venules, veins, and then the vena cava. Then these two veins will empty into the right atrium, and you start all over again. Because the left ventricle is pumping into the systemic circulation, it's bigger. It has to be bigger. So it is 8 to 10 millimeters thick, thicker than the right ventricle. Sorry, it's 8 to 10 millimeters thick. Right ventricle is 2 to 3 millimeters thick. That should tell you how much more work this one does relative to the right ventricle. So it's thicker, does increase work. And those muscular arterioles, those big arteries, they present greater resistance against which that left ventricle must pump. Okay, questions so far? Good. All right. Remington, the blood is received by the heart where? Right what? Right atrium. And Andrew from there goes to the? And then Corinne, it goes where? First it goes to the? No. First it goes from the right ventricle to the pulmonary. Thank you. Pulmonary arteries. Meredith, welcome back. From there it goes to the lungs. And Amanda goes from there, lungs to the pulmonary vein. Jacob. Pulmonary vein to the? Not yet. Not yet. It goes from the lungs to the pulmonary vein to the? Just look at this picture. That tells you. That picture will tell you. So this is the pulmonary vein, goes to the pulmonary arteries, to the left atrium. Left atrium to the left ventricle and out the aorta. All right. So rehearse this. Rehearse this over and over again. And hopefully you'll get an idea. Okay, let's talk about heart valves. Heart valves. The atrioventricular valves are different structurally, depending on which side they're on. The valve on the right side has 3 cusps, 3 flaps, 3 cusps. So it is a tricuspid valve. Tricuspid valve. The valve on the left side has 2 flaps, 2 cusps. It is the bicuspid valve. Bicuspid valve. Now, because the bicuspid valve looks a little bit like a bishop's mitre, it gets called a mitral valve too. So those are 2 names that are interchangeable. Mitral those are completely interchangeable. And since I am the king of very stupid mnemonics, here's my mnemonic to help you remember this. Go to the rat lab. The right atrium has the tricuspid valve. The left atrium has the bicuspid valve. Rat lab. Rat lab. Yes, I know it's silly, but hey, if it works, it works. The great vessels also have a set of valves. Now these valves have 3 flaps. Those flaps look like half moons or quarter moons. They look like semi-moons, so they're semi-lunar valves. Semi-lunar valves. Now, very often in anatomical parlance, the aortic semi-lunar valve just gets called the aortic valve. And the pulmonary semi-lunar valve just gets called the pulmonary valve. So if you hear someone talking about the aortic valve, they mean the aortic semi-lunar valve. So don't let that confuse you. Now, what are these for? If the ventricle pumps, blood goes into the great vessel, what's to keep it from going up, and as the ventricle relaxes, from coming back down. And you'd have this. Not very efficient, right? So when you pump, blood goes up, the semilunar valves are open, ventricle relaxes, semilunar valves shut. Now you continuously pump blood into those without them falling back into the ventricle. It increases the efficiency of the pumping. And you can see at least the pulmonary semilunar valve positioned properly in this cutaway here of that pulmonary trunk, which will then branch into the left and right pulmonary arteries. All right. The aortic valve would be right across from this, usually right about here. Now, the opening and closing of these valves is actually passive. It's in response to pressure differences. Don't get the idea that the valves kind of do have their own heart muscle and they kind of do this sort of thing. They respond to pressure differences. If the pressure in the atrium exceeds the pressure in the ventricle, they will snap open. If the pressure in the ventricle exceeds the pressure in the atrium, they will close. Ditto for the semilunar valves. If the pressure in the ventricle exceeds the pressure in the vessel, they snap open. If the pressure in the vessel exceeds the pressure in the ventricle, they snap shut. They are passive. They respond passively to pressure differences. Pressure differences.
Is there ever a time that they like have abnormal function and they stop responding to pressure differences?
Yes. The semilunar valves can be stenotic. If they're stenotic, they won't open all the way. And that would be one case where they don't work properly. And then the AV valves, most commonly the bicuspid valve, mitral valve, will tend to prolapse, so they won't close properly. And we'll talk about heart sounds. In cases like that, you'll hear what's called a click. And there's different types of clicks, and that tells you where the dysfunction is. So this kind of makes my point. The ventricles relax. Venous return of the blood in the atria will cause the pressure in the atria to rise. Eventually, the pressure in the atria will exceed the pressure in the ventricles. The valves will open, and blood will move from the atria to the ventricles. That will then cause the ventricles to fill. Eventually, the pressure in the ventricles exceeds that in the atria. Now those valves will snap shut. Then the ventricles will contract. When they contract, the papillary muscles pull on the chordae tendineae. That's going to keep those shut, keep those AV valves shut. That contraction now greatly increases the pressure in the ventricle, but the pressure in the vessel now is much lower, and now those semilunar valves will snap open, and the blood will be propelled into the great vessel. Then the pressure in the great vessel will exceed the pressure in the ventricle, and they will snap shut. The semilunar valves will snap shut. So those chordae tendineae, again, when the wall of the heart contracts, the papillary muscles contract, the chordae tendineae then pull on the valves. By pulling on the valves during contraction, they essentially keep those valves shut. Those valves will not open during contraction because they've got those cords essentially pulling them shut. So the blood then has only one place to go, into the vessel, not back into the atria, which would be counterproductive. And the semilunar valves again, they are open during ventricular contraction. Blood moves then into the great vessels, be it pulmonary or aorta, pulmonary vessels or aortic vessels. When the ventricles are done contracting and then they relax, now the pressure in the artery is greater than the pressure in the ventricle. Now those central inner valves shut in response to that pressure difference. That prevents this retrograde flow of blood back into the ventricles. All right, let's now look at a video that shows us cardiac cycle. Okay, what just happened? Okay, stop. All right, so you can hear this. Let's turn this on here. Good. And okay, now to view this, I have to do this. Okay, now let's give this a try. And you guys can't see that. Why can't you see that? Oh, good golly, Miss Molly. Okay, let's take two. Try again. That was a lot of information. All right, back to branch here. Okay. All right, so this, as it said in that video, this recurring cycle of contraction, relaxation, contraction, relaxation. That's called the cardiac cycle. The cardiac cycle. It consists of two phases, contraction or systole, and relaxation or diastole. Systole and diastole. Now, when we refer to contraction, relaxation, we are referring to ventricular contraction and relaxation. Very important point, because the ventricles and the atria don't contract at the same time. Most of the blood is transferred from the atria to the ventricles via pressure differences. When there's a little bit of blood left, the atria will contract and polish off that remaining blood. So you could potentially survive without atrial contraction. That condition is called atrial fibrillation. This is a very common heart condition. Now, it increases your risk of blood clots because you have more stasis of blood in the heart. And you usually have to go on some sort of anticoagulant or something like that. But by and large, this is a condition with the right treatment that you can survive with just fine. Systole is on the average of about 0.3 of a second. Again, on the average. Diastole is on the average about 0.5 a second. So the cardiac cycle in general will take about 0.8 of a second. That's going to vary from person to person. For example, an aerobic athlete will usually have a very low heart rate. So in that case, usually their diastole might be longer in cases like that. It just depends. But these numbers are very average. You can see as well, during diastole, you have this little interval here wherein the atria contract. During ventricular systole, notice that the atria are relaxed. Something to keep in mind. The right and left atria contract virtually simultaneously. The right and left ventricle contract just 0.1 of a second apart from each other. So when they are relaxed, that is the ventricles, they fill with blood. And as we said, the right ventricle contracts 0.1 of a second after atrial contraction. Left ventricle, 0.2 of a second, usually after atrial contraction. After the atria will fill with blood, and the pressure that exceeds in the atria exceeds the pressure in the ventricle, the AV valve snaps open, blood flows from the atria to the ventricles. The contraction of the atria will take the final 20% of the blood and will put it into the ventricles. So this is the amount of blood in the ventricles at the end of diastole. The ventricles are about to contract. This volume is called the end diastolic volume, the EDV. The end diastolic volume is a hugely important number for cardiac rehab because heart heals, you should start to see the ventricles tighten up. So you should see that number actually go down as the heart heals. You can measure EDV with an echocardiogram. And that will be usually a good measure of your cardiac rehab. So that's where that's a big, big importance to the cardiac rehab out there. The ventricles contract. They will eject a fraction of the blood. They won't eject all the blood. That fraction of the blood they eject is called the ejection. Most people will have ejection fractions in the mid to high 60s. If you've had a heart attack, your ejection fraction will go down substantially. Once your ejection fraction gets into the 20s and 30%, you're in deep trouble. Because it's a number that tells you if you've had a heart attack, how bad it is. 2, the heart can start to deteriorate after a heart attack, how much it's. The amount that the heart ejects during each contraction this is another number. In congestive heart failure, the walls of the heart start to stiffen and thicken. They get so thick now, they have very little space for blood. And that goes way down. So this is also a number about health of the heart under certain conditions. The amount of blood left in the ventricle after contraction, that's called the end systolic volume. The end systolic volume. Now, during cardiac rehab, would you expect that number to go up or down? Down. If your cardiac rehab is successful, you want less blood left in the ventricle. That tells the cardiac technician and the cardiologist your heart is beating more efficiently. So that's another number that should go down. Then the ventricles will relax and fill again. So here's just kind of some gee whiz numbers. Average cardiac rate is 70-ish, 75, 70, something like that. REM's probably in the low 50s, something like that. So those of you who are aerobic athletes, Corinne, I'm guessing you're, yeah, yours is probably pretty low too. I've seen you guys work out. You guys aren't slouches. Yeah, you guys work pretty hard. So I wouldn't be surprised if yours is in the low 50s. So each cycle will last 0.8 of a second. Half of that second is in half a second in diastole, 0.3 of a second in systole. When the heart is in systole, the pressure in the systemic arteries averages around 80 millimeters of mercury or 80 torr. 80 torr, that's an average. Your blood pressure varies throughout the day. When you wake up, it might be low. You have your first cup of coffee, probably jumps up a little. If you're like Andrew over here and you have 3 more cups of coffee, maybe jumps up a little bit more, and then maybe goes down. When you're running to class because you're late, it goes up. You hear the announcement, there's a test, goes up again. Then you remembered you studied last night, so it goes down. So it goes up and down, goes up and down. But the average diastolic pressure will be about 80 torr. The cardiac cycle has 6 phases. 6 phases. Let's look at those phases in some detail. Phase 1. So the ventricles contract. The pressure in the ventricle rises, but no valves have opened yet. So the volume in the ventricle is the same, even though it's contracting, but the pressure is increasing. So this phase is called isovolumetric contraction. Isovolumetric because the volume stays the same. Isovolumetric contraction, that's phase 1. So we're starting with the ventricles being filled, valves are all shut, the ventricle is contracting. Phase 2, the valves open. Which valves? Semilunar valves. They open, blood is ejected into the great vessels. This is the ejection phase. The ejection phase. The pressure in the left ventricle and aorta will rise to about 120 millimeters of mercury, 120 torr. If, let's say, John over here is running the bases, he got a nice base hit and he's trying to get to third, it's going to go up because he's barreling into third, right? So it's going to go substantially higher. Now, when he slides into third and gets up, is it going to stay up there? No, it's going to go back down. So this will be about the average. Ejection phase. The blood in the great vessels, is it going to stay there or is it going to flow through the vessels? Newsflash, it flows through the vessels. So the pressure in the vessel will fall eventually. But because the pressure in the vessel exceeds the pressure in the ventricle, the semilunar valves are going to snap shut. So we have the ejection phase. Now we have the semilunar valves closing. Semilunar valves closing. Pressure in the aorta now will fall down to about 80 torr. Pressure in the left ventricle falls to 0. The ventricles now have their valves shut and they're not filling, so they're not changing volume. This is isovolumetric relaxation. The atria, however, at this time are filling. So the pressure in the atria increases, but the ventricles now, this is their period of siesta. So phase 4 is ventricular siesta, or isovolumetric relaxation, if you want to be technical about it. But eventually, that pressure in the atria will exceed the pressure in the ventricles. Then the AV valve. Now the ventricles fill, and this is the phase of rapid filling. That's going to eventually start to raise the pressure inside the ventricle because the volume is increasing. Then you have atrial systole or atrial contraction. And the pressure in the ventricle exceeds the pressure in the atria. What does the AV valve do then? It shuts. That is your last phase. Now let's map these out versus volume and pressure changes in the ventricle. This is a table shamelessly stolen from your book. This is figure 13.7 on page 424. Figure 13.7, page 424. Go through this with me. Phase 1, isovolumetric contraction. Notice volume doth not change. Pressure increases and increases rapidly. Phase 2, ejection. Semilunar valves open. Now, volume drops, therefore pressure drops. Phase 3, isovolume, AV valves shut. So this is your second heart sound. That's your dub of your lub dub. Boom, and they get a heart sound. Phase 4, siesta. But it doesn't last very long. So then we're going to have volume changes when the atria open. Now you get rapid filling. Then you get contraction. And then you're going to get isovolumetric. You're going to go back from 6 to 1 again. And there we are again. And when the AV valve snaps shut, you get your first heart sound, the lub of lub dub. Yeah.
Based on this diagram, why is the majority of the sound in the first phase, not the second phase? If it's just when we talk about phase 1, it was just the pressure rising, not necessarily the valve.
Because that's essentially when you hear the sound. That's when you hear the sound, pretty much. And once they close, contraction begins immediately. And we can also interpose over this the EKG, which we'll talk about in just a bit. And we can see that the first heart sound occurs at the trough of the S, and then the second occurs essentially at the crest of the T wave. And crest of the T wave essentially is here, and QRS essentially is going to be in here. Now let's talk about heart sounds. If you use a stethoscope, you can actually hear the closing of the AV and semilunar valves. If we place our stethoscope between the second and the third rib, this is called the right second intercostal space. The right second intercostal space. You can actually feel for it. You go from here, you can feel off the sternum here, 1, 2, and that's your third right intercostal space. So if you essentially listen to these particular areas, so between the second and the third rib, just up near the upper border of the sternum, we can hear the closing of the aortic valve. That's on the right side. On the left side, we can then hear the closing of the pulmonary valve, same place, left side, but between the second and the third rib, the third intercostal space. Those would be the two places where you'd listen for the closing of the semilunar valves. Now, how is the heart positioned in your body? Is the position nice and straight here like this? No, it's kind of kicked over like this, right? Yes? So then, if you want to listen to the closing of the AV valves, you're not just going to go here and here, are you? You're going to have to account for the fact that the heart is tipped a bit in this direction, in most people. So let's say we want to listen to the AV valves. Now we're going to go to between the 5th and the 6th rib, between the 5th and the 6th rib. It's the left fifth intercostal space. The left fifth intercostal space in what's called the mid-clavicular line. The mid-clavicular line. What's the mid-clavicular line? So everybody feel up here at your clavicle. Now, the middle of the clavicle is right about here. If you draw a line straight down, essentially, that's your mid-clavicular line. If you get to where that intersects with your fifth intercostal space, that's where you're going to hear the closing of the mitral valve. That's where you hear the closing of the mitral valve. And then if we go between the fourth and the fifth rib, next to the left border of the sternum, that's the best place to hear the closing of the tricuspid valve. The tricuspid valve. All right? So where do you hear the closing of the semilunar valves? Third intercostal space, very good. Third intercostal space. Between the second and the third rib. On the right side, you're going to hear the who? Aortic valve. On the left side, you'll hear the blah, 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 pulmonary valve. Then to hear the mitral valve, you're going to draw the line down the midclavicular line, and you'll look for the, between the fifth and the sixth rib, the fifth intercostal space. There you're going to hear the mitral valve the best. Then for the tricuspid valve, it'll be between the fourth and the fifth rib on the left border of the sternum. Left border of the sternum. Okay, with me? Now what do you hear? You hear a lub dub goo. You've heard it before, probably. It's pretty unmistakable. So the first heart sound is usually called S1. S1, that's the lub, S1. That's the closing of the AV valves. S2 is the closing of the semilunar valves. The closing of the semilunar valves. Now, during inspiration, so when you get highly inspired, you're watching Avatar or something like that, you know. Inspiration is breathing in, we mean. Expiration, breathing out. Inspiration, breathing in. During inspiration, if you listen carefully with the stethoscope, the S2 sound will split into two sounds. The S2 sound will split into two sounds. Can anybody suspect why? So when you breathe in, what happens to the diaphragm? Does it come up or down? Goes down. Goes down, increases pressure, increases volume, decreases pressure, so air moves from high pressure to low pressure. So when you drop the diaphragm, you get negative pressure in the chest. That negative pressure brings in more venous blood to the right atrium and the right ventricle. So it takes a little bit longer for the right ventricle to squeeze that extra blood into the pulmonary artery. So it takes a little bit longer for the pulmonary valve to close. That is called physiological splitting of S2. Physiological splitting of S2. That's why your doctor will put the stethoscope on your heart and say, breathe, normally. That's what she is listening for. Physiological splitting of S2. Now, what if you have a lot of blood coming into the ventricles because of exercise? In a case like that, when the ventricles contract, you get blood actually bouncing off the sides of the ventricles, and the ventricles will actually vibrate a little bit. That makes an extra sound. That's called S3. S3. And that'll sound like a lub-da-dub, lub-da-dub, lub-da-dub. You'll hear this in trained athletes. You'll hear this during pregnancy. But S3 can also be a sign of volume overload, like during congestive heart failure. So that's why we put Remington on the track. We say, go, Ram, go. And Ram starts running, and he does a Bruce protocol, and it gets steeper and steeper and faster. And Ram is running for all his worth, and we put a stethoscope to his chest, and we listen. We're probably going to hear an S3 because he's a fairly well-honed athlete. But if then we go over to Arbor Oaks and we listen to some of their hearts, we hear an S3, that's when you start to say, uh-oh, because that might be a sign of congestive heart failure. Now, if you have a condition where the ventricles are too stiff, then they'll have to push extra hard to get the blood out. And in doing that, they'll create another heart sound called an S4. An S4. That will sound like instead of lub-dub-ta, 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 this will sound like a lub-ta, ta, lub-dub, ta, lub-dub, ta, lub-dub, something like that. That stiffness is usually a sign of chronic hypertension or pressure overload and severe hypertension. Then there is what's called an innocent murmur that you hear in children. This sound is a result of the heart walls being thin, and they vibrate with the rushing blood. And I actually have a recording of this I can play for you. I'm sorry, those of you on Zoom won't be able to hear this because I have to unplug my microphone to plug this in. So it's called a Stills murmur. Here. That is completely normal in most kids. It has a characteristic, it's between S1 and S2. You hear a crescendo and a decrescendo with this type of murmur. Again, it's completely normal, usually disappears by adulthood. If it doesn't, then you've got heart valve problems. That's usually what it means. Okay, and I think we're out of time. So we'll pick this up on Friday. Friday, you'll be chapter 13. Yep.
Dr. Bradovich, I have a question about my biochemistry homework that was due
Yeah.
on Monday.
Yeah.
Should I wait to turn that in till I'm in person, or do you want me to send pictures of it?
Just send it with someone.
How would I do that? I'm at home.
Can you mail it?
Yes, I will be at school on Monday. I mean, on Tuesday.
Okay, so that's almost a week.
Yeah.
I'd rather you mail it.
Okay. Sounds good. Okay.
Okay, gang.